This video is the first of a series where we're going to use rate data to show how we can calculate a great deal of information about rates of reaction as well as equilibrium. To run us through this, we have a reaction that is N2O4 gas in equilibrium with 2NO2 gas. And we assume that each direction is an elementary reaction. So an N2O4 breaks directly into two NO2s. Two NO2s combine directly into a single N2O4. This will make our mechanisms very simple, so their rate expressions are also simple. We have rate data at 25 degrees Celsius, where we place just starting material in half atmosphere, and we see what the pressure change as it reacts is over 1 second. And so we can actually measure how much N2O4 has changed. So the pressures indicated are the partial pressures of that N2O4. We do this also for a reaction where we put nothing but products into a container, a half atmosphere of products. We let it react for 1 second, and we see the change over time. We do this again at 50 degrees Celsius. There's a pressure of N2O4 solely placed into a container. How does that pressure change as it reacts over 1 second? And additionally, at 50 degrees Celsius, a reaction where we have nothing but the product, half atmosphere, and we see how its pressure changes over 1 second. This is idealized data. In a real setting, you take more data over a little bit more time. But for our purposes of exploring how we can relate our rate data to our equilibrium, this will be what we are working with. For this first video, we're going to use this data for initial rates, and we're going to find what the equilibrium partial pressure of N2O4 is going to be at 50 Celsius. Nothing in the data given to us is in any way related to equilibrium initially, but we know we want to use this data to solve the equilibrium pressure of the N2O4 at 50 degrees Celsius if we started with 1 atmosphere of starting material and no products. So we're going to put 1 atmosphere of N2O4 in. We're going to let it go to equilibrium. How much N2O4 is left? Now we're going to work through this, but if you want to pause and give it a try, by all means go ahead and do so now and then come on back. So how are we going to approach a problem like this? How do we take our rates and relate them to equilibrium? Remember that at equilibrium, your rate forward must equal your rate reverse. Well, what is our rate forward? It's going to be our starting material going to products. And we said these are elementary steps. So that means that the rate forward is some constant forward times, in this case, the pressure of N2O4 to the first. That has to equal the rate for the reverse reaction. Well, if these are elementary steps, 2 NO2s are going to combine to go backwards. So there's going to be some K reverse times NO2 squared. If we are at equilibrium, these two rate expressions must be equal to each other. The forward and reverse must be happening at the same rate. Well, we can reorganize this a little bit. We can bring K reverse down. We can bring the N2O4 down. We end up with that the K forward divided by the K reverse must be equal to the NO2 squared divided by the N2O4. So we just reorganize to get constants on one side and our pressures on the other. But this NO2 squared over N2O4, that is products over reactant to the power of their coefficients. That would be equal to Q, except that we're at equilibrium, so it's really equal to the KEQ. If we take our rates at equilibrium expressions and reorganize it, we can create the mass action expression for that reaction. Well, if that has to equal the ratio of our rate constants, the ratio of our rate constants must equal our KEQ. So if we can find our K forward and our K reverse, we can find our equilibrium constant. If we know our equilibrium constant and the starting concentrations of our materials, we can find our equilibrium values. So here's how we can take rates and relate them to equilibrium in a general sense. We need to do that for this data, which means I need K forward and I need K reverse at 50 degrees Celsius. So we're really only using the second half of our data here. So let's take that data at 50 degrees Celsius and let's find those values. Remember that our rate is going to equal K times the pressure of N2O4 for our forward reaction. Now this reaction, it's a single chemical. It just breaks apart. This is a first order reaction. So the forward reaction is just one chemical breaking apart. Being that it's first order, we can use the integrated rate law for the first order reaction. Ln of the pressure at initial divided by the pressure at time. All that must be equal to KT. We don't really have any specific rate info. Yeah, we have a little concentration over a little time. We could probably puzzle it out. However, we also simply know the amount the concentration changed versus time. We had 0 second and we had a 1 second. For a single second passing, we know the changes in the pressures. We can solve K. The natural log of 0.5 for the initial pressure divided by 0.492215, all that has to equal K times the 1 second time. This allows us to solve K forward. Integrated rate law is probably our easiest means to do this, since we know by the assumption that this is an elementary reaction, that this is a first order reaction in the forward direction. So the natural log of 0.5 divided by 0.492215 divided by 1 second is going to give us a K forward of 0.015692 per second. So we can find our K forward. If we want to do our K reverse, well, similar idea. My rate in the reverse direction is going to be equal to K reverse times the pressure of NO2 squared. Now this is not a first order rate law. This is a second order, which means we're going to need the second order integrated rate law. 1 over the pressure at time minus 1 over the pressure initial must equal KT. Well, I have my starting pressure. I have my pressure at time. So 1 divided by 0.495225 minus 1 divided by 0.5 must equal K times the 1 second time difference. We can solve for that K. In this case, we'll find that 0.019284 is our K. So we've got our K reverse and our K forward. Well, if we want to solve our K of equilibrium, that's going to be equal to our K forward divided by our K reverse. Here's a quick footnote. You'll notice that we have different units for our Ks. Equilibrium constants are unitless. So either our units need to fully cancel or there's something wrong here. And while we do solve out our rate constants with units, if we're trying to relate them to equilibrium, we need to take the activities of all these values. Remember that the equilibrium constant is always unitless, and it does it by dividing each concentration by the standard 1 molar or 1 atmosphere. And so back when we would have been doing the concentration components or the pressure components, we would have removed their units if we're going to relate it to KEQ. As a result, the units simply drop away as we do these calculations. What we'll find is that 0.015692 divided by 0.019284 is equal to 0.813741. That must be our equilibrium constant. It is our K forward divided by K reverse, redone as activities so that we don't have the units. And we find our K of equilibrium. Having our KEQ now lets us calculate out our pressures at equilibrium. We can imagine our reaction of N2O4 breaking into 2NO2. Initially, there's 1 atmosphere of our starting material and no product. There's some change of minus x and plus 2x. So at equilibrium, we'll be 1 minus x and 2x. 0.813741 must equal our products over our reactants. Well, that would be NO2 squared divided by N2O4, which in this case is going to be 2x squared divided by 1 minus x, or 4x squared over 1 minus x must be equal to 0.813741. So we can take our equilibrium concentrations, we can plug them in. We need to rearrange to solve for the quadratic. So we'll multiply 1 minus x over, rearrange everything. What we'll find is that 0 is going to equal 4x squared plus 0.813741x minus 0.813741. Solve out our quadratic. There will be an addition and a subtraction option. The addition option will be 0.36065. The subtraction options will be negative 0.564. Well, I can't have negative products in the end, so the subtraction route must not work. And so our answer must be the addition route. As a result, we can say 1 minus 0.36065 is going to equal the pressure of the N2O4, which is 0.639 atmospheres. So let's compare this with our rates. Our rate forward must equal our rate reverse at equilibrium. We now know the K value for our K forward. That was 0.015692 per second. And a concentration we now know of 0.639 atmospheres of our N2O4. All that had to equal our K reverse, 0.019284. I just realized an error. This is atmosphere seconds, not liters per mole. We weren't using concentrations. We were using atmospheres. So we need to adjust that discussion a little bit on our K value there, but placed it back in. Our concentration, in this case, is 2 times X. So that's 0.7213 atmospheres of NO2. 0.7213 atmospheres there for our product squared. So K forward times our starting material to the first power should equal K reverse times product to the second power. If we calculate this out, we'll find 0.01003 must equal 0.01003. With slight rounding, this was really 27 and this was 33. Indeed, our rate forward, given our K value and our equilibrium concentration, appears to equal our rate reverse times our equilibrium concentration of products squared. So despite using only a bit of rate data, how much the concentrations of the pure material changed over 1 second, we're able to use these relations and the elementary reaction steps to calculate out what the equilibrium constant should be based on the rate constants. Use that equilibrium constant to find the concentrations, or in this case, the partial pressures, of our product and our starting material. And we can even plug those back into our rate expressions to see that they do, in fact, come out equal to each other. Why does this work? Well, it really comes down to this relation right here. Why do you reach equilibrium? It's because your rates in either direction are the same. When your forward reaction and your reverse reaction are occurring at the same speed, that is when you are at equilibrium. While you can adjust your concentrations, eventually those concentrations will alter to the point where equilibrium is re-achieved. This is dependent on the K value, the constants between the two. The ratio of those constants determines where that equilibrium is going to lie. As you change your concentration of materials, they will adjust until the ratio of your constants again balances to KEQ.